What is the specific problem that the proposed method, Inheritune, aims to solve?
The proposed method, Inheritune, aims to solve the problem of efficiently pre-training small base language models, LMs, in a low-data regime. Specifically, it addresses the challenge of developing competitive small base LMs with just a fraction of the pre-training data available for larger reference models. Inheritune focuses on extracting a smaller target model from a larger reference LM by inheriting the initial transformer blocks and then further training it on the limited available dataset. This method aims to achieve comparable performance to larger models trained from scratch or derived from existing large base LMs, while significantly reducing the computational resources and time required for pre-training. Inheritune provides a cost-effective and data-efficient approach to developing small base LMs that can later be fine-tuned for specific tasks, making it a valuable solution for scaling down large language models.
How does the proposed method, Inheritune, work? Illustrate step by step.
The proposed method, Inheritune, works in the following step-by-step process. 1. Step 1. Inherit the first layers of the reference model. The target model is initialized with the first n layers of the large reference LM, where n is a chosen number of layers. The weights of the target model are inherited from the reference model, including the prediction head and token embeddings. 2. Step 2. Train. The target model is then trained for a given number of epochs, e, on the available training data, which is a small subset of the full pre-training data of the reference model. The training is performed with the available data, iterating over it for multiple epochs. 3. Step 3. Fine-tuning, Inheritune v2. In a slightly different setting where full access to the pre-training data is assumed, the smaller base LMs are developed by progressively exploring bigger sizes until achieving parity in validation loss with the original reference model. This step involves training the inherited model with the full pre-training data and evaluating its performance. 4. Evaluation. The performance of the smaller base LMs developed using Inheritune is compared to the reference models in terms of downstream tasks, such as common sense reasoning, natural language understanding, factuality, and language inference. The evaluation includes metrics like zero-shot and few-shot accuracy on various datasets. 5. Analysis and comparison. The derived smaller models are compared with models trained from scratch with significantly more data. The performance of the models is evaluated across different tasks to assess the effectiveness of Inheritune in developing competitive smaller base LMs. 6. Scaling and generalization. Inheritune is further analyzed with different choices of the number of layers, n, to understand its scalability and generalization across different model sizes. The impact of using larger reference models and more pre-training data on the performance of Inheritune is also explored. 7. Initialization and convergence. The method of initializing the smaller models with attention and MLP weights is discussed, showing improvements in convergence speed and final validation loss. The comparison with randomly initialized models highlights the advantage of proper initialization in the training process. 8. Implications and applications. The implications of Inheritune in developing small base LMs in a cost-effective and efficient manner are discussed. The method is presented as a potential baseline for pre-training pipelines aiming to create smaller variants of large base LMs, with considerations for depth and generalization.
What are the theoretical or practical benefits of using Inheritune in developing small base LMs?
The theoretical and practical benefits of using Inheritune in developing small base LMs are significant. The method allows for the efficient development of small base LMs by extracting a target model from a larger reference LM and training it with a small fraction of pre-training data. This approach results in competitive performance compared to base LMs trained from scratch or derived from existing large base LMs. Inheritune enables the creation of small base LMs with fewer parameters and layers, reducing computational resources and training time. The method shows that smaller models derived with Inheritune exhibit lower validation loss and similar convergence patterns to their larger counterparts, indicating efficient training and generalization. Additionally, Inheritune allows for the exploration of different model sizes by varying the number of layers, providing flexibility in model development. The approach also demonstrates the potential for scaling across different model sizes and datasets, showing improved performance with more available data. Inheritune offers a data-efficient and cost-effective way to develop small base LMs, making it a valuable technique for researchers and practitioners in the field of large language models.
How was the method validated or tested in the paper?
The method was validated or tested in the paper through a series of experiments and analyses. The authors introduced a pre-training technique called Maths-F Inheritune, which involved training a small-size target model extracted from a larger reference LM. They utilized OpenLLama3B as the reference model and extracted a target model of size 1.5b. The target model was further trained on 1b of training data for 8 epochs. The small base LM achieved 89% of average downstream accuracy on 9 different datasets and 94% of MMLU 5-shot score compared to the reference model, which was double in size. The authors thoroughly analyzed Maths-F Inheritune in different settings, including using a 50B subset of pre-trained data and larger reference models to demonstrate the generality of their approach. They also compared the performance of models derived with Maths-F Inheritune to models trained from scratch for double the number of training steps. Additionally, the authors conducted experiments with different choices of number of layers to investigate the impact on performance. The method was further tested with larger reference LMs and 50B data to observe the performance improvement with more data. Ablations were also run to determine the total number of epochs needed for training the small base LM effectively. The authors also explored the impact of reusing tokens for multiple epochs versus using fresh tokens. Furthermore, the performance of Maths-F Inheritune was analyzed in the presence of full pre-training data, comparing the smaller base LMs to the larger reference LM. The results and discussion section provided detailed insights into the performance of the method across various experiments and scenarios, showcasing the effectiveness and efficiency of Maths-F Inheritune in developing small base LMs.
What results were achieved with Inheritune in terms of downstream accuracy and MMLU score?
The results achieved with Inheritune in terms of downstream accuracy and MMLU score were significant. The small base LM developed using Inheritune achieved 89% of average downstream accuracy on 9 different datasets and 94% of MMLU 5-shot score compared to the reference model, which was double in size. Additionally, the small model showed comparable performance on average downstream accuracy of 9 tasks and MMLU 5-shot score compared to publicly available baseline models pre-trained with 50 to 300 times more data. The small base LM derived with Inheritune excelled in 7 out of 10 individual tasks, achieving a score of 90% or higher compared to the reference language model, which was twice its size and trained with 1,000 times more data. Furthermore, when compared to a model trained from scratch with 200B tokens, the Inheritune model matched 97% accuracy in all 9 downstream tasks and matched the MMLU 5-shot score.
What are the limitations or drawbacks of using Inheritune in practice?
The limitations or drawbacks of using Inheritune in practice include the fact that it requires access to a larger reference model and a small fraction of its pre-training data, which may not always be available. Additionally, the performance of the smaller base LM developed using Inheritune may not always match that of the larger reference model, especially in scenarios where the smaller model is trained from scratch for a longer duration. Another limitation is that Inheritune may not be as effective in scenarios where the functions the large base LMs aim to learn during pre-training are significantly more complex, such as in language models, compared to other models like neural networks and convolutional neural networks. Furthermore, The choice of the number of layers to inherit from the reference model in Inheritune may impact the performance and convergence speed of the smaller base LM. Lastly, Inheritune may not be suitable for scenarios where knowledge distillation or weight initialization techniques are preferred over model inheritance for specific tasks or domains.